Good morning, dear students. Myself, Dr. Priya, working as Associate Professor in Chemistry, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. In today's class, we are going to learn about plastics. Plastics are nothing but a category that is belonging to polymers. Polymers are of different categories. Normal traditional polymers will exist, and then plastics will exist, and then fibers will exist. Reinforced fibers will also exist. So likewise, conduction polymers also exist. So likewise, different categories of polymers are available, in which plastics belong to one category. And these plastics are again classified into two different types, thermoplastics and thermosetting plastics. So in today's class, we are going to learn about one category of polymers, that is plastics, and how many types are there, or in which way it is classified, and then what makes the difference between these two, and then few examples. So coming to introduction to plastics, plastics are defined as kind of polymers which were characterized by their property that is called plasticity. So what do you mean by plasticity means? If we supply or if you apply any kind of stress or force on the polymer material that is on its surface, then if it is involving in permanent deformation in its structure, then that kind of property is called plasticity. So these can be molded to desired shapes when subjected to some amount of heat in the form of temperature and pressure in the presence of a catalyst. So these are having some kind of engineering applications. So let us see what are they. So their fabrication cost is very low, that is their manufacturing cost, it is very low, and low thermal and electrical conductivities, they possess very low. Thermal means heat, and then electrical conductivities, and they are highly resistant towards corrosion property, and then resistant towards organic solvents. That means they are not able to dissolve in organic solvents, and they are highly resistant to corrosion. That means anti-corrosive properties they are having, and these are able to reduce noise and vibration in the machines. If these were used as a kind of a layer on the surface of any machine, then, or a kind of insulation, then these are able to reduce the noise and vibration regarding those machines. And plastics are considered to be the bad conductors of heat, and these are used to make handles for hot objects. Most of the plastics are highly inflammable in nature. So coming to the remaining properties, plastics are considered to be electrical insulators, that means they don't conduct electricity and find large scale usage in the electrical industry. Plastics are highly resistant towards chemicals, as we discussed in the earlier case, that is organic solvents, and towards atmospheric gases and all, these are highly resistant. Plastics are very clear and transparent, so they can be molded into beautiful colored objects. So directly we will switch over to types of plastics. On the basis of their thermal behavior, that is their processing, plastics are classified into two different types, thermoplastics and thermosetting plastics. That means whenever plastic materials were subjected to some amount of heat in the form of temperature, how they will behave, how they will respond, basing on that, that is thermal processing behavior, these plastics are classified into two different types, thermoplastics and thermosetting plastics. So what are thermoplastics and what are thermosetting plastics? Let us discuss one by one. So coming to thermoplastics, these are the resins which become soft whenever they were subject to heating process, and they become very rigid materials on cooling. If some plastic material it is subjected to some amount of heat in the form that is given in the form of temperature, then immediately it becomes very soft in nature, and then immediately it becomes very rigid material on cooling. So such kind of plastics are named to be thermoplastics. That means they are able to come back to their original form. That means they retain their original form. Such kind of plastics are named to be thermoplastics. But that is not possible with the case of thermosetting plastics. That means they do not become soft on supplying some amount of temperature, that is heat in the form of temperature, and they become very hard. So on prolonged heating, these are able to involve in decomposition and cannot get back to their original structure and form, and then they will continue to burn. They will start to continue to burn. So such kind of plastics are named to be thermosetting plastics. So what makes the difference between thermoplastics and thermoplastics in first point? So that means thermoplastics are very soft in nature when they were subjected to some amount of heat, and immediately on cooling they will become rigid materials. But that is not possible with the case of thermoplastics. That means They do not soften on supplying some amount of temperature. And if we prolong the heating process, then they start to involve in decomposition, and which are not able to get back to their original form. And also, if it is continued, then they will start burning. So that means, basing on this definition, we can come to a conclusion that thermoplastics can be reshaped and remolded. That is what we call as they can be reclaimed. That means there is no wastage for this kind of plastics, that is thermoplastics. But that is not possible with the case of thermosetting plastics. These cannot be remolded, and once they were manufactured, that their setting, it is permanent in nature. And coming to the third point, they are formed due to addition polymerization. Generally, almost all thermoplastics are produced due to addition polymerization, whereas in the case of thermosetting plastics, due to condensation polymerization reaction, that means due to elimination of small molecules, these kind of plastic materials will be produced. And thermoplastics will have very small molecular weights, and these possess linear structures, whereas thermosetting plastics are larger in molecules. That means they have cross-linking or 3D linking. That's why they possess high molecular weight with a cross-linking. That means three-dimensional network will be present in the polymer backbone. And thermoplastics consists of long chain linear polymers, which weak secondary van der Waals forces of attraction will be taking place between the atoms, individual atoms present in the polymer backbone. In the case of thermosetting plastics, highly cross-linked structure, that is due to strong covalent bonds presence in the polymer backbone. And that cross-linking is also due to the strength of covalent bond that is present. And thermoplastics are able to become soft on heating readily, because the secondary forces of attraction between the individual chain can break easily by supplying some amount of heat in the form of temperature, pressure, or sometimes both the conditions. So easily that forces of attraction, as they are very weak van der Waals forces of attraction, they involve in breaking process, so that with the application of heat in the form of temperature, these plastics are able to become very soft in nature. And coming to thermosetting plastics, the bonds retain their strength on heating, hence they do not involve in softening process on supply of some amount of heat in the form of temperature, because of presence of covalent bonds, and those bonds are able to retain their strength on heating, so they do not become very soft on supplying some amount of temperature in the case of thermosetting plastics. And thermoplastics are considered to be very soft, weakened, very less and brittle. Brittleness means a kind of mechanical property, that means easily broken. So that property is very poorly exhibited by thermoplastics, and these are very weak in nature. As I told you, these are having weak van der Waals forces of attraction in the polymer backbone, that is polymer chain. Hence, these are weak in nature. With the supply of some amount of heat, they involve in breaking process. And these are very soft in nature. These materials are very soft in nature. And coming to thermosetting plastics, which are more brittle in nature, that means easily broken, and these are very hard in nature, rigid, or we can say tough in nature, and very strong material. Thermosetting plastics are very strong materials. So, thermoplastics are usually soluble in organic solvents. Thermoplastics are a kind of resins which usually soluble in organic solvents. In laboratory, we will have different examples for organic solvents like ethylene dichloride, and then benzene, toluene, like that. Some polar organic solvents will be petroleum ether. So likewise, we will have different organic solvents in the chemistry lab. So these thermoplastic resins are generally they are able to dissolve in whenever they were immersed in organic solvents. Due to the presence of strong covalent bonds and 3D cross-linking in the polymer backbone of thermosetting plastics, these are not able to dissolve in the organic solvents. That means these are purely insoluble in nature in the organic solvents. Sometimes these involve in a process called bulging. That means if they were immersed in organic solvents, sometimes they will be involving in swelling process. That means that material becomes swollen. But it is highly insoluble in organic solvents. So curing process can be done, that is by adopting cooling process. Curing, it is done by cooling process. Curing means for making that plastic material as a rigid or tough one or hard one. So for that, this engineering materials are subjected to curing process after their manufacturing. So here it is considered as curing process, that is by supplying some amount of less temperature, that is cooling process we have to subject for. Examples for thermoplastics include polythene, polystyrene, polyvinyl chloride and Teflon. Coming to thermosetting plastics, this curing process can be done by subjecting to some amount of temperature and pressure. So then only that material becomes very hard, or we can say rigid and tough in nature. Examples for thermoplastics include, or thermosetting plastics include bakelite, polyester and silicones. So in our syllabus we have bakelite. So this is about different category of polymers, that is plastics, and plastics are again subcategorized into two types, thermoplastics and thermosetting plastics. Its definition, introduction, and then examples we discussed. Go to example for thermosetting plastics, that is bakelite. So in our syllabus we have preparation, properties and engineering applications of bakelite. It is nothing but phenoplast or phenol formaldehyde resin or phenoplast. It is an example for thermosetting plastic material, and it is how it is produced, what is its synthesis, what are its properties, general properties and applications. Let us see one by one. So how this bakelite it is produced? It is produced due to condensation of phenol and formaldehyde. What is phenol? Phenyl ring which is having OH group, that is what we call it as phenol. This is phenol, and it is formaldehyde. If these two were subjected to condensation polymerization. So what do you mean by condensation polymerization? A polymerization reaction takes place due to the elimination of small molecules like HCl, water, ammonia. So due to the elimination of any of these molecules, if it takes place, then such type of polymerization reaction is called condensation polymerization reaction. So this phenol and formaldehyde, when subjected to condensation polymerization reaction, bakelite will be the product, condensed product. So it is prepared by condensing phenol with formaldehyde in the presence of either acid or base, acidic or basic catalyst. That's why here it is mentioned like H+. So for this process to take place, either we have to make use of acidic or basic catalyst. So phenol and formaldehyde react to form their corresponding methylol derivatives. So this is purely dependent upon the ratio, how much ratio you are going to consider. So here these two are considered to be the monomers, phenol and formaldehyde. If I take 1:1 ratio, that means equimolar ratios of phenol and formaldehyde were taken. That means 1:1 ratio. Then the product will be orthohydroxy methylol phenol, or we will call it as methylol derivative of phenol. Orthohydroxy methyl phenol. See, this is the functional group that is attached to carbon, and this will become as the alpha carbon, and this is what we call it as ortho position. Ortho position, if it is vacant, ortho, meta, and this is para. So priority will be given to ortho position first. Later it will go to para position, and then third one it is of meta position. So first which will be occupied due to this treatment of phenol and formaldehyde using 1:1 ratio, that methylol derivative will be produced, and which is going to occupy at its ortho position. So this is ortho position occupied because of 1:1 ratio, or para position also can be occupied. There are two different chances. So if I take 1:2 ratio, 1:2 ratio, here again we will get one more substitution, CH2OH. So this is dihydroxy methylal phenol. So because it is having two different substitutions. Next, if it is like 1:3, if I take 3 moles, 1:3 ratio, then para position also will be blocked. Here we will get one CH2OH, here also we will get a CH2OH. That is trimethylol derivative of phenol will be produced. So for this bakelite formation, we are going to consider only 1:1 ratio of phenol and formaldehyde. So as a result, we will get orthohydroxy methyl phenol as a product. So then it is subjected to this orthohydroxy methyl phenol is able to react with phenol. So if it is again subjected to this orthohydroxy methyl phenol that was produced in step 1, if it is taken in n number of moles and treated with n moles of phenol, that is first monomer, then what will happen? Due to condensation polymerization reaction, elimination of water molecule will take place. Here water molecule is going to eliminate. That means this phenyl ring will have, this carbon will have one hydrogen. So, and that is going to be eliminated in the form of water molecule along with the OH minus ion that is present in the methyl or derivative of phenol. So, as a result, if water molecule is going to eliminate, so then what will happen here? CH2 we have. So, as this is going to eliminate, this bond is going to link with carbon. So, this ortho position, again it is having a linear chain will continue. So, what is the name of this compound? Novolac. Novolac is a linear polymer. Straight chain linking will be there. So, that will be the result in step 2. Step 1 is formation of orthohydroxymethylphenol. How it will be produced? By considering 1:1 mole of phenol and formaldehyde in the presence of either acid or base catalyst, then it is able to produce orthohydroxymethylphenol. This orthohydroxymethylphenol, when subjected to treatment with phenol again, then it is able to form a linear polymer which is named as Novolac. So, this is the structure of the linear polymer Novolac. So, this produced Novolac is having a properties like it is highly soft in nature, it is fusible, that means easily mixes with another type of compounds, and it is also soluble in organic solvents. So, this produced Novolac, if it is treated with polymerizing agent, that is HMTA. HMTA stands for hexamethylene tetraamine. So, if this Novolac is treated with this HMTA, HMTA is nothing but a kind of polymerizing agent which is able to create a 3D network in the polymer backbone. So, this Novolac when treated with the HMTA, that is polymerizing agent hexamethylene tetraamine, then it is able to form one pink colored, hard, infusible, insoluble solid, that is what we call it as cross-linked organic polymer bakelite. So, initially Novolac is a linear polymer that is produced in step 2. It is a white colored solid mass which is very soft in nature, and it is fusible in nature, and it is soluble in organic solvents. If that Novolac, it is again treated with hexamethylene tetraamine, that is HMTA in step 3, which is a polymerizing agent, then it will result in the formation of a baby pink colored, pale pink colored product, solid mass, that is what we called as bakelite. See the structure of bakelite. So, up to this extent we know that is the structure of Novolac. Then what will happen with the help of HMT? So, it is going to get a cross-linking like this, cross-linking. So, this is what we call as 3D network, and it is named as bakelite. It is named as bakelite. So, this is formation of bakelite. So, it includes 3 different steps. Step 1 is formation of orthohydroxymethylphenol. It is produced due to treatment with the phenol and formaldehyde which were taken in 1:1 ratio. And then this obtained orthohydroxymethylphenol, this one is able to combine with phenol again. So, as a result, it is able to form a linear polymer that is called Novolac. So, this Novolac on treatment with HMTA, that is hexamethylene tetraamine, which is a polymerizing agent, which is able to form bakelite, that is a cross-linking, it is produced in the bakelite structure. So, let us see the properties and applications of bakelite. So, generally this bakelite will possess the following properties, that means, as I told you, it is also known as phenolic resin, phenol formaldehyde resin, and it is example for thermosetting plastic, it is named as phenoplast, and then it is produced due to phenol derivatives. In this synthesis, or we can say preparation of bakelite, we are going to make use of phenol derivatives. That's why it is named as phenolic resin. Phenolic resins are very hard, rigid and strong materials, and they possess very excellent resistance towards various chemicals, atmospheric gases, and highly resistant towards heat and moisture content. So, these are being attacked by the alkalis, that is basic materials, because of availability of free hydroxy groups in the structure. So, if you notice the structure, it is having availability of free hydroxy groups. So, because of this hydroxy groups, it is able to get easily attacked by the alkalis in the nature. So, and coming to the applicative part of bakelite, So it is having lot of applications, which is considered to be a very good electrical insulator. So that's why it is having applications in towards manufacturing plugs which were used for domestic purpose, switches and switchboards, and then it is also very much useful in molding the articles that were related to radio and television cabinets, that is electronic components, radio components, and then TV and television and radio cabinets. Molding also it can be done using bakelite, and it is used as one of the ingredients in paints and varnishes. Generally, paint is considered to be a mixture of different ingredients like vehicle drying oil, pigment. So likewise, resin will also play a major role. So this bakelite is also a very good example as one of the ingredients that can be added in the paints. Same thing will be applicable for varnishes also. And then we know very well. So it is also used in ion exchange process, which is meant for purification of water, that is hard water. So in that we can use this bakelite as an example for anion exchange resin. So and then as it possesses very good adhesive properties, it can be used as an adhesive or binding or binder for grinding wheels. So binder means it is able to fuse all the things, or adhesive means it is having that adhesive properties. So for grinding wheels and all, we can apply this bakelite as an adhesive or binder. And during the manufacturing of bearings, propeller shafts, and also in paper industry and rolling mills, this bakelite is having lot of applications in the required areas. So for impregnating fabrics, wood and paper also, we can make use of bakelite. So let us see some examples. This is a switchboard, as I told you, and these are the handles which were used for carrying hot objects. That means some kind of objects which can be used like household purpose utensils and all, pans and all, frying pans and all. They will have a very high temperature. Their working temperature, it is very high. If such kind of hot objects we just want to hold with our hands, it is very difficult. So for that we can make use of this handles which are manufactured using bakelite material. So these are the knobs used for gas stoves and all for domestic purpose. And so this is example of anion resin. This picture reveals it is a resin or a kind of material which can be used in ion exchange process as anion exchange resin. So and if you notice, the bakelite is having also some examples in ornamental purpose also, that is manufacturing of some kind of bangles which are meant for ornamental purpose. So these are the applications of properties and applications of bakelite. So in today's session, so far what we have discussed is introduction to plastics. Plastics are nothing but a category of polymers. How many types of plastics are there? There are two different types: thermoplastics and thermosetting plastics. And coming to thermosetting plastics, we have an example in our syllabus, that is bakelite. For bakelite, its introduction, and then synthesis, properties, and applications we have discussed. In the coming session, that is in the next session, we are going to discuss about the very other category of polymers, that is conducting polymers. So how many types are there, how they can be classified, and few examples for conducting polymers. So that's all for today's class. Thank you.